Welcome back to AIT 2101. This is the 5th installment of our vibration analysis lecture. We're going to jump right into it. No need to really rehash it, but our last episode or our last video lecture, we talked about the equipment used to pull the vibration data from the machine into the data collector so we could look at it and use it to determine what's going on with our machine, the health of our bearings and components and things like that. Okay, so when we look at it though, if you remember, I showed you the hacksaw blade, okay, and we get that deflection, okay, and that energy there that we can capture. We can capture that same type of energy with our data collector, but it goes beyond that. It takes that data, and this is this spike energy right here, and that doesn't mean a whole lot to us. It gives us some idea that it's vibrating. It gives us the peak at which, peak information, and that's kind of hard to read, okay? But what the data collector does, and the software of course too, is it takes this spike energy and it converts it to a fast Fourier transform wave, okay? That's basically the spikes that we see along our spectrum, not spike energy, but these spikes within this spectrum. And down below is the frequency at which the vibration is occurring, okay? So this translated to an FFT down below. This is our 1 times RPM, okay, or cycles per minute here. And this is 1 times, so we've got a little bit of imbalance probably going on here. I'm not sure what the 2 times is there. Could be misalignment. But what we have right here, what was real interesting, is this. You can't read this on the screen, I'm sure. It says vane pass. This is for a pump. This is for the filter pump. And this is measuring the vibration data coming off of a pump. And the pump has vanes on the impeller, okay? And here we got vane pass frequency. And most likely what's going on here is, as we have talked about before, every vibration is a derivative of its driven force, okay? The driven RPM. So we have multiple vanes on there times is the result of the number of vanes times the running speed, and we wind up with a vane pass frequency. So we can tell that something is rubbing one of the vanes in that pump, or the vanes are rubbing against something inside a housing or something, and it's giving us a frequency that we probably need to take a look at. Okay, so but this is a little bit cleaner version, and you can see there's spike energy going here, not spike energy, excuse me, but the peaks of our amplitude and our frequency or our data. Okay, so there are some characteristics that are behind these spikes that the data collector will take a look at. So we're going to go by, take a look at each one of these. The first one is frequency. The next one is displacement. Then we're going to look at velocity or the speed, and then also acceleration. All right. So let's look at frequency first. That's the one thing that I keep talking about a lot. Okay. We've talked a little bit about it in previous lectures. But vibration frequency is a period of vibration. This is the amount of time for one cycle of that vibration to complete. Okay, that's the amount of time. All right, that's the period of vibration. Now the vibration frequency is how many of those cycles are within a given period of time. In electrical units, we talk about hertz. How many cycles, AC cycle sine waves are crammed into 1 second? Okay, that's hertz. But the vibration community tends to look more at cycles per minute. Okay, so we have our beginning of our cycle here, and there's the end. That's 1 cycle. And if this is our time, it could be from peak to peak as well on the positive side. But if this is our 1 minute time, this is 1 cycle per minute. That's pretty slow. Okay. If we have 1,800 of these as our running speed of a motor, we'll have 1,800 cycles per minute within this 1 minute time period. So that's kind of how we come up with the vibration frequency in cycles per minute, as opposed to hertz like the electrical community uses. All right, it's just a lot easier to translate, to talk about, and to understand. So we use cycles per minute. Okay. Now, knowing the vibration frequency, or its signature as it's often called, gives us an idea of where our source of problem is coming from. Okay, a piece of equipment that has bearings and gears and is driven by an electric motor, it can have tons of different frequencies. You saw the vane pass frequency on a pump. So one machine can have multiple vibration frequencies. And you got to look at them and know where these frequencies are coming from in order to identify and pinpoint the bad component. Otherwise, you're kind of guessing at it, and you're going to look bad. When they tear apart down, it's perfectly good, okay? So vibrations will always be a derivative of the rotational speed of the machine, whether it's the 1800 RPMs of the motor or the shaft, the input shaft of a gearbox. All of them are going to be derived from the input speed on the driving speed of that machine, okay? And from there, like I said, it's just kind of the process of elimination. You try to find what's, like if you have let's say you have 30,000 cycles per minute vibration that's really showing a spike on your spectrum there. You know, you're not going to look at the 1800 RPM motor because that's not what's vibrating. You're going to look at what might be running at 30,000 cycles per minute, and probably something with your gear mesh if you're looking at gearboxes or things like that. But like I said, it's the process of elimination. Okay, like I said, frequency pinpoints the vibration and its source, where it's coming from. We also, that spike that you see also looks at vibration amplitude. Okay, this tells us about the severity of the vibration, and that really, depending on the machine that you're looking at, that can vary from it being just fine to, oh, we got to rebuild this or replace some components. Kind of talking about this a little bit, it gives us an idea of how bad that vibration is. For example, we may have a blower fan, okay, that's used in the process, but some vibration in that fan is okay. It can be fine. However, if we took that same amplitude of vibration and it was the same amplitude coming out of, say, a lathe or a mill that's used to make very, very precise products, it's completely unacceptable. So whereas one machine might be fine with a certain amount of vibration displacement or amplitude, it may be catastrophic for something else, okay? And it's not unacceptable. So we have that vibration amplitude, okay? That's how much displacement there is from peak to peak, okay? So the vibration amplitude tells us about the severity, and the displacement is simply the total distance in our sine wave, total distance from our peak on one side to how much it bends or flexes down to the other side, or rotates or goes down to the other side. Those two on each side of that horizontal line is our displacement, our total displacement, or our peak-to-peak displacement, okay, from one extreme travel to the other. And it's like I said, it's also known as peak-to-peak displacement, excuse me. And we measure that in mils, in 1,000ths. If you are from the top to the bottom of your sine wave, that's 1,000ths of an inch. It's known as having 1 mil of displacement, okay? So again, 1 mil is equal to 1,000ths of an inch. So if this is exaggerated, so if my arm is that shaft and I'm vibrating up to here and I'm going back down, that's how much displacement I have. If it's 1,000ths of an inch, if that is 1,000ths of an inch, that is 1 mil, okay? So that, again, from here to here, that total displacement is peak to peak, all right? And really, you're not going to see this, but I will hand this out in the mandatory in-person lab that everybody's going to be coming to. What this does is it gives us an idea of whereas it might be very smooth running at 400 or 500 RPMs or cycles per minute. Okay, that vibration might be considered very smooth. However, if we run it at a much faster, higher RPM, for example, in a lathe or something like that, then we're looking at this being kind of slightly rough, in the slightly rough category. And then we convert this to inches per second. That's how far it would travel if we were to put it in a linear path. But this chart, and again, we'll go over this more in lab, but this chart gives us an idea, is the bearing smooth or is it rough? Is the vibration and that displacement, is that considered rough, very rough, extremely smooth, very smooth? It really depends on the application of the machine. And we'll look more at that when you come into lab, but we'll take a look at that chart. Okay. The other component that makes up that spike that we see on our data collector or our software when we're analyzing the data in our offices is the velocity. That's the speed at which the vibrating component is moving back and forth, the speed in which it goes from top to bottom in our sine wave, okay? And it's constantly changing, and we'll show you that in just a second. Maximum velocity, though, the maximum speed is what we're using for our measurement purposes, okay? Because, again, we've got a wide range of speeds throughout that sine wave. we are going to look at maximum, it looks at maximum velocity for its measurement, okay? So when we have our amplitude, okay, this is our peak, okay? When we get here, kind of look at it like if you were on a swing, okay, and someone pushes you, and you go up, and at some point, you peak, okay, and you start going back in the reverse direction, okay? Well, where you peak, you actually come to a split-second stop, whether you realize it or not, but you come to a complete stop, then you reverse directions. Kind of the same thing's going on here. You go up here to complete top, and that's when our speed is at its lowest. We will actually come to it, that shaft will actually come to a stop, standstill, and go in the other direction. You can't see it with the naked eye, but trust me, it's happening right here. And this is the range, this is constantly changing. The speed is 0 right here, and then we pick up and we pick up and we go faster and faster. And it's at this point, this intersection right here with this horizontal line, that we are at maximum velocity. And again, that's the speed at which the data collector picks up on and uses to calculate the measurements used in that spike. Okay, so now we're slowing down, and we're going to come to a dead stop here. That would be our swing kind of coming back in this direction. We're going to be at a dead standstill, and then we're going to take off again and hit maximum velocity right across that intersection of that horizontal line. So that is that's the velocity. Now we also look at, with the machine, the data collector also looks at acceleration. Now acceleration is the rate of change in velocity. Okay? For example, you're sitting at the stoplight, you take off, that's when your acceleration is at its most. Okay? You're driving down the road at 60 miles an hour, flat surface, you're on cruise control, and there's absolutely like 100% flat surface. You're not accelerating at all. You got velocity, but you have no acceleration. So just like velocity, the maximum acceleration is what the data collector would use to determine the acceleration. And we measure that acceleration in G's. G-force is the Earth's gravitational pull. How much gravitational pull the Earth provides is considered 1G. Anything above that is a multiple of the G's. You're talking about jet pilots pulling 4 or 5 G's or something like that in their jet. That's the amount of Earth's gravitational pull multiplied by 3 or 4 times, okay, and that their body is subjected to. Well, the same thing goes on here. The machine is subjected to the acceleration, how quickly that moves through that sine wave. So that's measured in G's, okay? So quite the opposite, though, at the top of our sine waves, this is where our acceleration is at the most. This is when we're accelerating the most, and right here is where we're kind of like flat and cruising down the road. At this intersection, our acceleration is at its least amount. Of course, we get here and it repeats itself again. So that is the elements that the the vibration data collector is looking at and analyzing when it creates those spikes. Now, I've got one more lecture for you to look at, and we're going to take a look at how that energy that we just talked about is finally put into play, and how we look at different frequencies and can kind of identify what components in our machine are going bad. So anyway, that concludes this lecture. Be sure to look at the next one. And again, if you have any questions, by all means, come and find me, and we'll talk through them, okay? Thanks a lot for your time, and we'll see you